last week, we talked about failure in materials, right? We talked about how materials can break from just exceeding the strength that the material is made for. So the material can break if the force you're placing on it exceeds the strength of the material. The material can also break when forces are less than the materials are designed, from fatigue or creep. So fatigue is from many, many cycles of use, and creep is when you have a constant stress, but you're using the material at elevated temperatures. And we know that materials break because of crack formation and crack propagation. So materials that can plastically deform can prevent the crack from growing very quickly. Eventually, cracks will still grow if you continue to use the material or if you continue to apply enough force to break the material. But materials that are ductile, that can allow for plastic deformation, will be able to accommodate some of those cracks. So it will slow down the crack propagation and not break as easily. Materials that are brittle don't have a way for plastic deformation, and therefore once the crack starts to propagate, it grows very quickly and will break very quickly. How does plastic deformation occur? So we know that plastic deformation is useful to prevent crack propagation, but what is plastic deformation? So what happens in a material that allows for plastic deformation to happen? Perfect. Yes, the breaking and reforming of bonds. Another way to look at it or talk about it is slip or dislocation movement, right? And so because of slip, materials are able to deform plastically. So in order for slip to occur, you have to be able to break individual bonds and form new bonds. We know that in ceramic materials, this is not usually possible because the bonds in the ceramic material are either covalent or ionic and covalent, and they're very, very strong. So it takes a lot of force to break it, but once it's broken, because of the localized electrons, it is very difficult to reform. Okay, so ceramic materials are usually brittle. I put a paper in your supplemental readings in the E3 portal that talks about a ceramic material that can be plastically deformed at room temperature by up to 20%. So it has a strain of up to 0.2 before it breaks. This is a paper by a group of scientists led by Zane, and it was published in the journal Science in October 2022, so very recently, just last month. What they found was that they are able to make a ceramic material, silicon nitride, Si3N4, that can be deformed. So we know that ceramic materials do not allow for slip. So how does this particular material plastically deform? So at room temperature, you're able to deform this material, squeeze this material by up to 20% strain. Okay, so it's a big amount. It's something that is visible. And this material does not allow for slip. So what happens is that instead of slip, so there is no slip in this material, but what it has instead is that it has two phases, alpha and beta. So phases are crystal structures, the way the atoms are aligned. And they're quite complicated to draw, so I'm not going to draw alpha and beta, but if you look at the paper, it does have a schematic of what alpha looks like and what beta looks like. So silicon nitride has two phases, alpha and beta. There are different crystal structures, but have very similar lattices. So the size of the unit cell is similar. The atomic lattice between the atoms are similar. So you can have, let's say, a boundary where you have one kind of crystal structure and a boundary with a different crystal structure. This is just for example. Okay? But the edges of those crystal structures will line up because they have similar atomic lattice. And so what happens when you squeeze this material is that one phase will transform into another phase. And I can't remember right now if alpha goes to beta or beta goes to alpha. I think beta goes to alpha, but you could check the paper. One phase will transform under pressure. That energy that you're supplying by pressing the material will cause one of the phases to transform into a different phase. And that transformation allows for bonds to be broken and then reformed one at a time, just like in slip movement, right? So it's the same idea that the bonds can be broken and then reformed, broken and then reformed. And that's how this material can allow for plastic deformation. But instead of using slip, this material uses phase change. So the phase change. So this is the first material to have ever been reported to be able to do this. Okay, it's a brand new phenomenon that's never been observed before. And I think if you look at the paper, the link, you might be able to find links to videos showing them squeezing the ceramic material and the ceramic material being able to deform without breaking. It's quite interesting. So the next topic I'd like to talk about is phase diagrams. Phase diagrams are a really important tool for material scientists. And when we saw that video of the gentleman that was making the Wootz steel in Florida, and he was working with a material science professor to figure out, exactly what was happening within the steel, they were looking at phase diagrams because I was helping them figure out exactly what kind of phases are happening within the steel. What should they be able to expect? Okay, so phase diagrams are diagrams that show thermodynamically stable phases. This is really, really important to remember, is that phase diagrams only show thermodynamically stable phases. Thermodynamically stable phases are phases that are at their lowest energy state. Cannot go any lower. That's why they're stable. So thermodynamically stable phases are what is being represented on phase diagrams. So it doesn't tell you what will happen between you making the material and the material going to its most stable phase. It might go through a series of changes before it gets to the most stable phase. The phase diagram does not tell you what is happening before it gets there. It only tells you what is there once it reaches its lowest energy state. Okay? But even so, it's still very, very useful for material scientists. So material scientists use the phase diagram a lot, okay? Especially for metals like steel and aluminum and other kinds of alloys. So in order to talk about phase diagrams, there's quite a bit of vocabulary that we need to get through. Just like when we were talking about unit cells, we needed to understand the vocabulary behind unit cells. We need to understand the vocabulary behind phase diagrams. So the first one is, what is a solution? So a solution is made up of two or more components. You can have a liquid solution. A liquid solution is very common, like if you put salt and water, if you have solid salt and liquid water, that's not a solution. That's a two-phase mixture. But once the salt dissolves into the water, then you have a homogeneous mixture of salt, NaCl and H2O, right? It's completely mixed, so that's a liquid solution. You can have a solid solution. You can have, like steel is carbon inside iron. It's not carbon and iron separately. It's carbon mixed evenly into iron, so that's a solid solution. So solution doesn't mean that it has to be liquid. It could be solid as well. Solvent is, I hate these definitions because it uses another thing it will define in the definition, but this is how it's defined. Okay, so a solution is made out of two or more components. The solvent is what is dissolving the solute, and the solute is what is being dissolved in the solvent. So basically, if you have salt water, the water is a solvent, and the salt is the solute. If you have steel, iron is the solvent, carbon is the solute. So the component that is a lot less, usually we say that that's the solute. And the component that's where the crystal structure or the phase is not changing, that is the solvent. And usually there's a lot more solvent than there is to solute in a solution. An alloy is a solid solution. It's a metal made of 2 or more components. And so iron is an alloy because it's steel is an alloy. Because it's made out of 2 or more components, it is made out of iron and carbon. And carbon is the solute that dissolves into the iron that's a solvent. And the way it dissolves into the solvent is through interstitial or substitutional sites, right? That's how the carbon goes into the iron. The iron structure doesn't change, and the carbon goes into the iron either into interstitial sites or into substitutional sites. And components are just the parts of a solution. So in a salt water solution, the 2 components are salt and water. In a steel, the components are carbon and iron. So solubility limit is the maximum concentration. So solubility limit is how much solute can you put into a solvent without changing the structure of the solution. So you know that if you're adding sugar into water to form a sugar solution, you can add so much sugar that eventually the sugar crystals will no longer dissolve into the water, and you will get crystals of sugar that comes out that are left over. That doesn't dissolve, right? So now you don't no longer have a homogeneous solution because you've exceeded the solubility limit. So same thing can happen in solid solutions. You could put so much carbon into the iron that you could form a new phase or have something different come out. And that's what that gentleman from Florida, that's what Alfred Pendros, anyway, that's what he made with the Wootz steel. He put so much carbon into his iron that he was making carbides, iron carbides. So that's a different phase that has a different material characteristics that he was forming with his steel. So he exceeded the solubility limit of carbon into iron. Phase is part of a system where, so a phase is a part of a system where all the properties are the same. So if you have a salt solution where all the salt is dissolved in the water, that salt solution has one phase, right? Because throughout the solution, everything is the same. It's all the same salt water. But if you exceed the solubility limit and some of the salt becomes crystalline and comes out of the solution, now you have 2 phases. You have the liquid salt water phase, and you have the solid phase that is just salt, NaCl. So you can have 2 phases. When we start talking about solid solutions, you can have many, many phases. Okay, and we'll talk about that in a little bit. Mixture is system of 2 or more phases. An equilibrium, it's a thermodynamically stable state, which means the system is at its lowest energy state at given conditions. These conditions could be temperature, pressure, concentration of solute. So obviously, a material, a system, can be at its equilibrium at one temperature, but if you change the temperature, the equilibrium phase will be different. So an example of that, so let's say you have a wooden block. So you have a wooden block and you balance that wooden block on its edge. This is an unstable state. So we'll call that condition 1. You can imagine that you could balance that wooden block very, very carefully, and it could stay there for a small amount of time. But any amount of disturbance will cause that block to fall over, right? you can have the block sit like this. This is called a metastable state. So condition number 2, this block will sit here for a long time, but it is not at its lowest energy state, right? The lowest energy state is this way. So this is a stable state. Condition number 3. So if we were to look at the energy, let's say this is state 1, 2, 3, something like that. The system is at its highest energy state here. It's unstable. It's at a lower energy state here, and it's at its lowest energy state here. So let's say we have something like this. And so there's no energy barrier between 1 and 2. It'll just fall over. You don't have to do much. Right? So energy decreases as it goes from state 1 to state 2. State 2 is metastable, meaning that it could stay there for a long time. In order to get to the lowest state, it needs some energy input, right? You need to push it so that it falls over. So you can imagine that there's like an energy barrier between 2 and 3, and then 3 is the lowest state. So a phase diagram will only tell us what is the third state, the most stable state. A phase diagram, you will not see this as a possibility, because a phase diagram only tells us the thermodynamically stable state, or the equilibrium state. It does not show us the metastable state. Okay, so that's important to remember when we're looking at phase diagrams. So let's look at some examples of phase diagrams. So this is a water phase diagram, and it shows us the different phases of water at different temperatures and pressures. So the x-axis is temperature, the y-axis is pressure. And water exists in what we usually consider 3 different states: gas, solid or ice, or liquid, right? There's actually a 4th state, which is beyond the critical point. So if you see temperature 374 and pressure above 22,000 kPa, kilopascals, you have something called the critical point, or C. Beyond that, you have a supercritical state. That's what it's called, because it's above critical. Supercritical state of water that is neither a gas nor a liquid. It exhibits properties of both. So there is actually a 4th state. We just don't usually see it because it takes so much pressure to get there. Most materials will have this. So carbon dioxide, CO2, also has a gas, liquid, solid state, and then also a supercritical state. And in fact, when I was doing my doctorate, my PhD, a lot of my work involved the use of supercritical carbon dioxide to make different materials. Okay. So it is used, it's just not commonly, we don't see it in our everyday life. So this is a phase diagram. We can see what is the most thermodynamically stable state at any given temperature or pressure. Okay. That doesn't mean, so let's say you have water here. So we have temperature, something like here, and pressure is 1 atmosphere, well, okay, something here, okay, where you have liquid water, and you heat the water up, and at this point, you would expect the water to boil, right? So if you keep the pressure constant, you have liquid, and you continue to increase the temperature, you expect the water to boil right here. And in fact, usually it takes a little extra temperature for the water to boil, because that's the thermodynamically available state. It doesn't happen right away. So usually you can wait there for a long time, and eventually it will boil. But if you increase the temperature a little more, then it'll actually boil a lot faster. So this diagram doesn't tell you the rate, how fast things happen. It just tells you what is the most stable state at that temperature and pressure. And same thing, if you go the other way, you cool the material down, you will eventually get ice. Okay. But right at the transition point, you may not get that much ice. You may have to lower the temperature a bit more. So that's for water. This is for iron. So not steel, this is just iron, just Fe. So you can see that iron at fairly low pressures and low temperatures, so anything below, say 600 degrees Celsius, exists in the ferrite phase, which has a body-centered cubic structure. And let's say we keep the pressure constant, we increase the temperature, eventually it will convert into a face-centered cubic structure, and then you keep increasing the temperature, it will become a liquid. Or you keep the temperature constant, but you increase the pressure, so you squeeze the iron, it will go from eventually from body-centered cubic to hexagonal close-packed. Okay, so by looking at these diagrams, it tells us what to expect when we heat treat iron, right? If we heat iron and we want carbon to go in, we know, well, in BCC, carbon usually would go into the substitutional phase, but in FCC, carbon will go into the interstitial phase. So probably it's easier to put carbon into the interstitial phase because there are more interstitial sites. So we want to heat iron up to 1,000 or more degrees Celsius because then carbon goes in more easily. So that's very, very useful for us to have that information. Okay, so before we go on to more complicated systems, which I will show you, let me talk about what happens when you have more than one component. So the water and the iron phase diagrams I showed you were just single component phase diagrams. Let's look at binary or two component phase diagrams. So this is temperature on the y-axis in degrees Celsius. And the x-axis is the weight percent of nickel in copper. So here is 100% copper, and here is 100% nickel. Nickel and copper have very, very similar atomic lattices. They have the same crystal structure, and the size of the atoms are very similar, and they have similar electronegativities. Those two elements are very similar to each other, and so they could substitute for one another in the substitutional sites from 0% to 100% without changing the structure of the solution. So you have, let's call this an alpha phase. So down here, I actually don't remember what copper is. I don't remember if it's like a body-centered cubic but it has a crystal structure, and nickel has the same, and they can substitute in each other and with varying degrees of concentration and still have the exact same crystal structure. So we call that alpha. That's an alpha phase. This is solid. You take it to a high enough temperature, it will melt. So you have liquid, and 100% copper melts at 1,085 degrees Celsius, and 100% nickel melts at 1,455 degrees Celsius. Okay, so they do have different melting temperatures. And in between here, between the liquid and solid, you have a region where you have both. You will get both liquid and solid phase. So there are a couple things that we need to learn about phase diagrams so we could talk about it more easily. The line that separates the solid, 100% solid phase from the mixed phase is called the solidus line. And the line that separates the liquid, the 100% liquid from the solid and liquid mixture is the liquidus. And let's say I have 3 points on this phase diagram. This is 50% here, 50% nickel, also 50% copper. Point A at 20% nickel. This is C. Okay, I have 3 points, A, B, and C. So for point A, what phase do I have? Liquid, right. I have the liquid phase at point A. It's 100% liquid. What is my composition of my liquid phase? What is that liquid phase made out of? Any questions about how to read what is present at point A? Okay, let's look at C. What is my phase here? What is it? Alpha, right. 100% alpha. What is my composition of my alpha phase? My point B is a little bit different, so let me show you. So for C, I'm going to expand the phase diagram a little bit so it's easier to see. Okay, this is liquid, this is alpha plus liquid. Everyone see, I'm just drawing this smaller section here. Okay. All right, so what phases do I have in point B? Alpha and liquid. By just looking at this, do you know what percentage I have of, in my mixture, how much alpha do I have and how much liquid do I have? Can you guess which one is more? Would you guess at this point, do you have more solid or more liquid, you think? Probably more solid because it's closer to the solidus, right? And further away from the liquidus. So had just started, you're taking, if you assume that you're keeping the concentration of nickel constant and you're raising the temperature, it's solid, 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 it has just started to melt because you're just past the solidus line. So some of it started to melt, others are still solid. Most of it is still solid. So that's what we would assume. So if we look at something called we draw a horizontal line across. So constant temperature. We draw that line across. We bring that down. This line crosses the liquidus, happens to be at 30%, and crosses the solidus at 55%. And this is 50 weight percent nickel. Okay, so this is, it crosses the liquidus at 30 weight percent nickel. It crosses the solidus at 55 weight percent nickel. All right, so the weight percent of liquid phase, it's equal to the distance of that line to the opposite phase. So if we were to call this length between the liquidus line to where our material is, R, and this distance, S, the amount of liquid is the distance to the opposite phase. So S divided by the entire distance of that line. So S would be 55 minus 50, and the entire length of that line would be 55 minus 30, and that would give us 0.2 or 20 weight percent liquid. We should be able to know, based on this, that we have 80 weight percent alpha because our mixture only has two phases. So if we have only 20% liquid, then the rest must be alpha or solid. But let's calculate that anyway, just to make sure. So alpha, same thing. You take the material going to the opposite phase. So for alpha, because it's solid, we go to the liquidus line, where the line crosses the liquidus. So that would be 50 minus 30, divided by the entire length of that line, 55 minus 30, and that is 0.8 or 80 weight percent. The composition, now this is a little bit, you have to, I guess, just remember this. The composition of the alpha, so let's say we look at this mixture at point B. We look at this mixture under the microscope. We might look something like this. These are alpha. And in between, you have 20% liquid. The composition of the alpha phase here is not 50% nickel and 50% copper. It is the composition of where that line meets the solidus. So the composition would be 55% nickel and 45% copper. And the composition of the liquid at point B would be the composition where that line meets the liquidus. So it is 30% nickel and 70% copper. So if you have 20% of your material made out of a low nickel component, the liquid, and 80% of your material made out of a high nickel component, adding them together and averaging that out, this mixture will have 50% nickel and 50% copper. But the individual components are not 50-50. Okay? So whenever you have a mixture, the composition of the phase is where the horizontal line meets the single phase component. We'll talk about this more. I'll give you more examples so that will be a little more clear as we go on. Okay?